I want to talk about work that I did here with Javier, one of the organizers here, Javier Magan, and Temple He, a student of Andy Strominger, who is on the postdoc market. And there's a follow-up paper by Simon Gentle, who's postdoc in Utrecht. And it is about entanglement entropy for scale-invariant theories that are not relativistic. So I encoded it by Lifshitz entanglement. And so in the past decades, of course, we have learned a lot about entanglement entropy, both for strongly coupled field theories using Ryo Takeyanagi, but also, and that has even a longer history, for weakly interacting field theories, in particular even free theories. There's very nice results for conformal field theories in low dimensions, etc. And so I want to try and investigate, in fact, most of the story, pretty much all of my talk, is going to be about free field theories and that have scale symmetry, Lifshitz scale invariance, where, let me see, this is the pointer, where time and space coordinates scale differently. And there's a dynamical exponent that is called z. And generically, you can think like, what is the entanglement entropy of such system as a function of this dynamical exponent? Is there still area laws and, or not, or under which conditions for z is there area law? And the free field theories are based on Hamiltonians, which consist of particles which have modified dispersion relations, and the dispersion is given by omega equals momentum to the power z. And so one can build quantum field theories based on such particles, and the prototype in 1+1 dimensions is a free scalar field with Hamiltonian given by this formula here. So the spatial derivatives we have higher derivatives here in the spatial derivative, and so we have pi is the canonical conjugate momentum of phi. This theory is scale invariant if you associate a weight to phi that also depends on the dynamical exponent. So most of the talk is actually going to be about computing entanglement entropy for this simple system. And so for z equals 1, of course, we have the relativistic case, and all my formulas should be reproducing the known formulas for entanglement entropy for relativistic conformal field theories. I will also be adding mass deformations to this theory, and I will in fact also later on do flows between two Lifshitz theories with different values of this dynamical exponent. So there's related work, mostly by the Iranian group here in two recent papers. In fact, Ali Molabashi is somewhere here, and I've been discussing also a lot with him here. And then there's earlier work on Lifshitz entanglement for particular values of z, namely z equals 2. Of course, that's a special case, by the group of Fradkin, and also more recently Tom Faulkner has been working on these topics. And so we've benefited also with discussions with these people. Good. So what are the methods to compute entanglement entropy in these systems? Well, it's actually not so easy. So one thing one can do is to discretize the model, put it on a lattice, and try to compute it brute force by correlation methods, for instance, and do a diagonalization. And that quickly involves numerical methods. And we have done these things, and we're going to also contrast this with another method that is the topic of my talk here. I'm going to use techniques that were developed in, well, a few years ago based on cMera and cMera, and then I'm going to add a little bit of holography or holography-inspired methods, and we'll see how that goes on. Now, these techniques, the continuous version of cMera is still something that is under development, and later on top of it, I'm going to use some holography-inspired methods that allows you to associate metrics to it. I'm going to use Ryo Takeyanagi kind of proposals. So not all of that is like completely settled, but I'm going to ask you to just hold in your breath and let me extract the prediction from it, and then we can compare that with the numerical methods and see how well it does and how and where it fails. So we'd certainly like to have more analytical methods, for instance, a replica trick, but that also is not so easy for other values of z. We don't have all the nice conformal field theory methods and twist operators, at least not as far as I know. And so, but maybe some progress could be made there. We haven't given this much thought. Good. Whereas most of the talk is going to be on free field theories, let me just make one comment about strongly coupled field theories. There one can use the standard holography method and Ryo-Takeyanagi. This is the Lifshitz metric. And you see there where when we concentrate on the ground state or entanglement entropy in the ground state, on static states, then we fix a time slice, and then nothing depends on z anymore. So the holographic prescription, at least in static states at 0 temperature, will not show any dependence on z, and you'll get the same answer as for ADS. You can try to put a black hole in it or do some hyperscaling violating, and then you get non-zero, or you get dependence on z. And there's some nice work also here done by Gonzola Toroba and collaborators, Gartrou et al. But I will not be talking about this. It's somewhat strange to see that there is no z dependence in the entanglement, because if you go back to this free field theories, if I discretize this, then discretize the derivative, it just produces a nearest neighbor interaction. If you get a higher derivative, then it produces next to nearest and even further correlation. So the larger z gets, the larger the correlations become, or the larger the interactions. You get long-range interactions. And you would definitely think that entanglement entropy depends on the correlation length, or not the correlation length, but the long-range interactions. But that can get washed away at large n or at strong coupling. I don't know. Good. So let's get started and say a few things about the cMera techniques. So cMera basically was developed in 2011 by the Ghent collaboration, and so I will say a few things about this. And a little bit later, there was an interesting paper by Nozaki, Ryu, and Takeyanagi, and I'm sure Tadashi can explain that much better than I will. And title of the paper is Holographic Geometry of Entanglement, Renormalization, and Quantum Field Theories. Basically, what they are doing is, in one sentence, they associate to a cMera quantum circuit a metric using an extra renormalization scale, and these metrics can then be used, or I will use them to compute entanglement entropy with the prescription of Ryo-Takeyanagi. So let me say a few words about this. So the cMera technique is somewhat similar to the discrete version of it. You start with a reference state in the infrared. It's an unentangled state, and you apply unitary operations to go to a final UV state, the Mera state, which for my purposes, I want it to be the ground state of the conformal, of the Lifshitz theory that I'm studying. And in the discrete case, the Mera network consists of coarse graining operations and disentangling operations if you flow from UV to infrared. And so that is mimicked in the continuous version by a scale operator L and a disentangling or an entangling operator K. It's somewhat a little bit similar to the kind of procedure that Rolf was talking about, except here that the parameter that I'm using to build up all these gates is the RG parameter U, the scale parameter U. And so this disentangling operator is going to play a crucial role in my talk. And so what Nozaki, Ryu, and Takeyanagi did was they constructed metrics of this type here, with metric components GUU and GTT. GTT is not specified in this talk, also not in their paper, at least not in the first version. If we're interested in just static or entanglement entropy in time-independent state, this part of the metric component is not important. And so the UU component of the metric is determined as a function of this disentangling operator. This disentangling operator contains parameters. Let's say you do a variational procedure to to minimize it, to find the ground state eventually, and then that is what these people did, and then you can get concrete expressions for this GUU. Of course, that's a long story, which I'm basically summarizing. It's a technique that can be used and that can be made very concrete for free field theories. And for free field theories, it turned out, that was the outcome of this paper, that if you have the data of the quantum field theory, and in particular the dispersion relations, if you know the dispersion relations, there's a very concrete prescription how to get this metric component GUU. You take omega as a function of k, compute this derivative, and replace k by e to the u divided by the cutoff epsilon. So this is maybe not supposed to work in full generality, as the authors also write, but for free fields, that can maybe give a qualitative understanding of how entanglement entropy can be computed and behaves. So let's just do it. I'm still surprised why actually the authors of the paper, I should ask Tadashi later, why they didn't make the exercise that I'm about to make here. Let's test the proposal for the case of relativistic free field theories. Then the dispersion relations are these. The metrics that are coming out are in fact already in the NRT paper. So this is basically just for m equals 0, it's the ADS metric in Poincaré coordinates, and this is just the gapped ADS metric that has been well studied. We know that this basically gives the right answer because that is essentially already in the original Ryutaki and Agi papers, but I'm just for pedagogical reasons summarizing it here. You can compute geodesics, and sometimes you get connected and sometimes disconnected curves, and you have to study who wins when. I'm not going to show or explain the figures. And so it reproduces the well-known results here. For the massless case, it produces the area law. The area law in 1 + 1 dimensions is a logarithmic law, and the central charge is C over 3. And so in the massive case is a little bit more subtle because the mass scale sets a correlation length, and we're always looking at entanglement entropy in a line interval. That's my subspace or subregion. And so the correlation length can be either smaller or larger than the length of the interval. In case the correlation length is smaller, then you can use this prescription and you reproduce back the well-known result for the entanglement entropy that Cardi and Calabresi found. So that's just reproducing known things. When the correlation length is much larger, then you get a different answer. I didn't write down the precise formula because we don't have, it involves more numerics. But it does not reproduce the right answer. Now, this is something that maybe not all of you know. For correlation lengths which are much larger, there is this work done here by Cassini and Huerta. There are terms here that involve logs of logs times m times L, or m times epsilon. And that's found also by analytic methods. But the cMera metric is not reproducing these things. So in these cases where the correlation length is much larger than the length of the interval, the cMera technique, at least not with the disentangling operator that was used, is not producing this formula. So there's going to be some limitation. So I'm going to stay out of this regime. Good. So let's go now to the new stuff. The new stuff it's essentially turning the crank here. We do now Lifshitz scalar fields. We have the dispersion relations. It's just omega equals k to the z. We plug it into the NRT proposal, and it spits out metrics of this type here. And so here's the only place where there is z dependence is here. Now you have to redo the calculation of finding geodesics and computing the lengths. That's again using standard methods that probably all of you have done sometime in the past. And if you do this for the Lifshitz case, you get this formula here. This is the length of the geodesic that ends on the endpoints of the line interval. So this is an exact formula, at least for computing the geodesic. And so there's two places where we see z dependence, here in front of the log, and then there's z dependence over here. And so the length of the geodesic is not quite the entanglement entropy. If you do ordinary holography, you find the entropy by the length, you divide by 1/4 g Newton, and then you use that g Newton gives the central charge, and then you have the entanglement entropy. Here, of course, this is not ordinary holography, this is just a way to geometrize entanglement entropy for free fields. And I don't know what g Newton is. So to get the entanglement entropy, there's going to be an overall coefficient which is independent of L, but it can depend on Z, and I don't know what this coefficient is. So I'll put it in front here, and I'll call it the Lifshitz central charge, C of Z. And so this was the length of the geodesic, and I multiply it by CZ/3. For Z equals 1, then C of Z is just, for one scalar field, is just equal to 1. And so this coefficient here, we can only determine it by numerics, at least that's the situation today. And we're in fact still producing numerical plots. I've been discussing this with Ali here. And for Z equals 2, for instance, you get, for instance, 3/4. And so we've also been finding this value in other papers in the literature. Now, let's see, this is not obviously an area law, and the area law depends on actually whether this ratio L/Z epsilon is large or small. So in the case where L is much larger than Z/epsilon, then, well, we can drop the 1 and we get the area law. So for small values of Z, large values of the interval, you produce the area law here, and the area law has a coefficient here, which is Z, times the Lifshitz central charge, which we can compute numerically. For larger values of Z, you get actually, it's interesting what happens. For larger values of Z, this ratio becomes small. If this ratio becomes small, you can drop it here. You get 1 plus L epsilon. You approximate the logarithm. You get just L/Z epsilon. This Z cancels this here, and you just get linear in L. That's a volume law. That's intuitively also what you expect, because if you discretize the theory, I was telling you that if you discretize the derivatives, you get long-range interactions. And the entanglement entropy usually comes from correlations just across the boundary of the interval that are entangled with each other. But if the correlations are much larger, then all the points in the interval will correlate and entangle with points outside of the interval. So you would expect actually a volume law to show up rather than an area law. And it's nice to see that the cMera technique and the NRT approach reproduces this. So, so that is the volume law. That was also explained in the paper by the Iranian collaborations. And this statement, of course, that you get volume law for very large values of Z holds also in higher dimensions. So if you plot this here, this is just the analytical plot of this formula, and we are still checking whether it fits perfectly with the numerics or not. And this part of the graph fits perfectly with the numerics. This is actually where we determine C of Z. And so the numerics indeed reproduce the area law. And so the constant can be read off from the numerical data. And here we have, the numerics is still underway, but the data that we have so far also show very good agreement here. For Z equals 2, you cannot really get good, you don't see the volume law. But if you plot for higher values of Z, you can also see indeed out of the numerics the volume law coming up. So this part of the curve is also going to fit the numerics. So then we're still fighting with an overall constant coefficient, but that is not so exciting. So we're actually pretty confident that this is going to lead to the full analytic answer once we kind of know an analytic formula for this Lifshitz central charge, which we don't have at present. So we can generalize the cMera technique is not confined to 1 plus 1 dimension. You can go to higher dimensions, and one can do the disk, but here for this talk I've just decided to do the strip. And for the strip, we generalize also known results for Z equals 1. You can compute these geodesics again, or surfaces, and compute their areas. And for large values of Z, you get two terms. One depends on the cutoff, and so you regulate the volume of the strip. That's V, And then there are some formulas that are very similar to the original Ryo-Takeyanagi paper, except that we extended for higher values of z. And so this term here is independent of the cutoff, and therefore it's a universal term. Here's the formula for kappa. And there's all kinds of factors of z, z to the power d. And one can check this also against numerics. This we haven't done. And for large values of z, our cMera formulas also produce the volume law. Here we have just the length of the strip times the volume in the other directions, and it's multiplied, so it's the overall volume of the strip. So that comes out of the cMera approach as well in any dimensions. And if you do it for the disk, it's similar. Now, so that's the case where we have full scale symmetry. We can add a mass term and do mass deformations, and it's still a free theory, so we know the dispersion relations. The dispersion relations is omega squared equals k to the 2z plus m. Now, out of the parameters here, we can find one combination that has the dimension of a length, that's psi here, so this is the correlation length for Lifshitz theories, alpha over m to the power 1 over z. And so now you can again go to the regime where the correlation length in the Lifshitz is smaller than the length of the interval, and then you can generalize the result by Cardy-Calabrese to other values of z, to higher values of z, and the result is very simple. It's again the log of the correlation length. Of course, in this correlation length, there's powers of z in here, so sometimes by notation you can make things too simple. So there is m to the 1 over z here, and then again there is this Lifshitz central charge here that that needs to be determined by numerics. So this is an interesting extension of the Cardy-Calabrese result for massive Lifshitz scalar fields. And so the next and last thing that one can do, how much time do I have? 5 minutes, perfect, yes, is to study other kind of flows more than mass deformations. We can here do, I remain working with Gaussian or free field theories, but now I add here two kinetic terms. One has a critical or dynamical exponent z, the other one is the relativistic one, and so compared to this term, this one is irrelevant in the infrared. So in the infrared, you have essentially a Lorentz invariant conformal field theory, whereas in the ultraviolet, this term is unimportant. This term dominates. You get a Lifshitz theory. So you can study the flows if you want from a Lifshitz field theory to a relativistic field theory. Or if you put here two different z's, then you can just flow between z1 and z2. I think you understand the kind of game that we're playing. And so these are the dispersion relations. And you can wonder, does the entanglement entropy decrease along the flow? Is there a C-theorem, which for the purpose of this meeting, I called CH-theorem, the theorem that was proven by Cassini and Huerta to work for relativistic cases. The question is whether, at least in these examples, the C-theorem also holds, namely the entanglement entropy decreases along the flow. There are counterexamples in non-relativistic theories where this C-theorem does not work, but these are, of course, very special versions of it. They're scale invariant, and there's no Fermi surfaces or anything like that. So you can repeat the exercise and see what the cMera technique produces. And so here are the plots. Everything works fine. Here we have k, and it involves alpha. So for large values of alpha, we are in the ultraviolet here, and for small values of alpha, we're in the infrared. And so the entanglement entropy, this is the length of the geodesic, but this we just divide by this overall factor. It decreases along the flow, and these are just for the different colors are just different choices of the length of the interval. So this is just as a function of the coupling constant. Here is this sort of similar plot, but now as a function of the length interval, and now the different curves are different choices of alpha. And when we go from UV to IR, then we see from the top curve we go down. These are all the kind of area laws here. and here we get linear behavior, volume loss here, but everything decreases as you go from ultraviolet to infrared. So actually, these are all kind of meaningful results, and so let me conclude that we have almost an analytic formula for the one-dimensional case, at least, an analytic formula for Lifshitz free scalar field theories. We need to, in fact, still find an analytic formula for this central charge. Maybe some replica method or other methods will produce this for us, I don't know. And perhaps equally interesting is that we've kind of tested this cMera and the NRT proposal, which is actually working much better than expected. And so that is maybe also encouraging to study and use this cMera and NRT techniques for other circumstances. One of the things that came to my mind this morning is whether these metrics, in fact, can be used to study things like complexity. But that is just one idea that I got this morning. So thank you for your attention.
We have some time for questions.
Yeah, thank you. I missed a very basic thing. So what is known from direct density matrix computation and free theory, say for z equal 2 in 1 + 1 dimension?
For z equals 2, there's very few things are known, at least for the case of free fields on a line interval. The area law is known, and the coefficient 1/2 is known. That's studied by the Fradkin group.
So they did see the logarithmic behavior?
They did see the logarithmic behavior, yes. Yeah. And that's, well, of course, the Fradkin group, they did many other things, like playing with other geometries. Maybe Tom Faulkner can also comment about this.
I know in the SALT paper they looked in 2 + 1 of the at the circle.
Yes, there's some results for the disk. We haven't compared our results beyond 1 + 1 dimensions with the z equals 2 case and the disk.
But is there some simple argument why you always get a log for any z?
Well, you don't. That's the point. Because for large values of z, the log turns into...
I fix z and make L large, right? It's a funny limit to be taking z bigger than L or something.
Well,
if you just fix z to any number and then make L large, is it believed that you should always get a log and not log squared? And not, what's the...
I don't have anything super intelligent to say about this, or I don't have any...
And from numerics, it may be even hard to see...
That's right.
In other words, is there something like this old Wilczek argument for the log?
That could be. I don't know. I don't know.
No. Okay, thank you.
Thank you. Interesting.
Any more questions?
In the back.
Sorry.
It's just a small question. Do you know if the CZ, your coefficient, is it related to the anisotropic trace anomalies in Lifshitz?
I hope so, but I can't confirm, yes.
But do you have like specific cases that you can...
Yes, we haven't given this enough thought yet because we were so much occupied with numerics and then understanding all the cMera business that I forgot to this important question. It's also not entirely clear to me whether it's the central charge or the anomaly coefficient should be this C or whether it's C times Z. So I hesitate a little bit to do this.
Thanks.
Any other questions? Okay, let's thank Stefan again.
Thank you.